Welcome to this lecture. In this lecture, we are going to talk about limiting behaviors of measurable functions. So, in the previous lectures of this week, we have introduced the concepts of measurable functions and Borel measurable functions, and we have also seen many algebraic properties which were also discussed specifically in the previous lecture. So, using such properties, we can construct many examples from existing examples of constant functions, indicator functions, and continuous functions. Okay. So, with that at hand, we are now going towards looking at the limiting behaviors of measurable functions. So, as usual, I will move on to the slides. So, when we have already discussed the algebraic properties, we have fixed these measurable functions on one specific measurable space. So, again, we follow the same procedure. We are going to fix the measurable space right at the beginning. We will be looking at real valued or extended real valued measurable functions, Borel measurable functions, and we will like to figure out certain limiting behavior for such functions. So, the setup is that we will be considering a sequence of such functions which we write it as fn subscript n, and we want to see whether their pointwise limit makes sense, and if yes, does it have some nice properties. So, suppose that each fn is real valued and Borel measurable, and then consider functions of these forms g and h which are given as pointwise limit. So, g is given as pointwise limit. So, for each point in the domain, small omega in the domain, you look at the pointwise limit. So, this is a sequence of real numbers and you are looking at the limit value of that, and that's how the function g is getting defined. Of course, this can be defined only if the pointwise limit exists for all possible such small omega. But instead, you can also choose to look at this supremum function on each omega. So, for each sample point omega, you first evaluate the values fn and then take the supremum. Now, you have to be careful that while you are considering the supremum, it might so happen that the supremum of this sequence of real numbers may be infinity. So, originally when you are trying to look at this function h from omega to r, you might have to consider the point plus infinity as a possible value there. Okay. So, this you have to take care of. So, then even though the original functions are real valued, g and h are limit pointwise limits and the supremum functions, they might take values in the extended real line. So, as such, for whatever discussions that we are going to perform or whatever discussions we are going to make, we may as well take the functions fn to start with to be extended real valued, and then discuss the properties, and then the function g and h can automatically be thought of as functions from omega to the extended real line. So, with that setup at hand, let's see the first result. So, it says that if you have this sequence of functions, but now you are taking extended real number valued functions. So, for such functions, if you assume that the pointwise limit exists, so this is an assumption because it need not exist, so in which case you cannot do anything there. But suppose it exists for all sample points small omega, then you can choose to define this function g as done above in the motivation. So, you define it as pointwise limit value. Okay. So, that's how you get the function g, and it turns out this result states that this also has to be Borel measurable, provided each fn that you have taken is Borel measurable. Okay. So, that's a nice property. So, how do you prove this? So, the technique is now quite simple. You go back to this note 13. So, just to quickly recall what this result suggested was that you choose a class of generating sets on the range side. So, on the range side, we have the extended real line together with the Borel sigma field on the extended real line. So, here what you do? You choose a collection of generating sets there. So, for that we have chosen intervals of this type, open x to closed infinity. So, remember we are looking at the extended real line where plus and minus infinity points are already there. So now we are looking at this type of sets, my open X to closed infinity, and these sets generate the Borel sigma field. So now what you are interested in is to check whether the pre-image of these sets will be on the domain side sigma field. If that happens, then by the result mentioned in note 13, you will claim that G is measurable. So that is basically the target. So let's try to figure out what is the pre-image of this interval under G. So it means that you have to look at all points in the domain, all points small omega in the domain, such that G of omega falls in open X to closed infinity. And that can be written as this simple inequality that G of omega is strictly greater than X. Okay, so that's a nice observation. So now let's look at this set. So all sample points small omega such that G of small omega is strictly greater than small x. So you have fixed an X arbitrarily now, and you are going to look at such sets. But then put in the definition of the function G. So that is nothing but the pointwise limit of the fn's. Okay, so let's put that in. But then if this limit value is strictly greater than X, you have already assumed that the limit exists. So that's a hypothesis in the statement. So you have already assumed that. So if this is strictly greater than X, then what you can say is that your actual value of the limit is something like some X plus epsilon, correct? And then all the values of the fn's, the sequence of values, that will not fall below the value X plus epsilon, right? So it can happen for only finitely many such things. Otherwise, if it happens for an infinite such collection, then you will get a limit which is smaller than X, right? So you can just choose to look at the inequality that is suggested by a limit. So therefore, after a finite stage, the values of fn will cross the values X plus some epsilon, correct? So now what you can rewrite these values epsilon as 1 by m format, right? So then you choose all possible such m from 1 to infinity, so all positive integers, and choose this x plus 1 over m, this kind of points. So if it happens that fn of omega, fn at small omega exceeds this value, then of course the corresponding limit will exceed the value small x, and this is an if and only if condition, right? So you for finitely many n, first few many n, this inequality may not hold, but then afterwards, after a certain stage, if this holds, then the limit is forced to be greater than small x. Okay, so that's the idea here. So you have rewritten in terms of the individual small fn from the limit statement, right? But then you have now written is in terms of a countable union. So now our target is to write down or describe this set here in terms of explicitly the fn's. Okay, so we are going to rewrite this, but then observe that for every fixed small m that you are looking at, this set here can now be thought of as the limit infimum of certain sets. What are these sets? That except few finitely many n, your value of fn of small omega that exceeds this value. So therefore look back in the discussions in week 1. So now you can go back to this description of limit inferior of sets, and you will immediately say that okay, so that means that this is the limit inferior of these events or this kind of sets. So what are these sets? That fn of omega exceeds x plus 1 over m. Remember, limit inferior simply implies that fn of omega will exceed this value for all but finitely many n. So fn of omega will exceed x plus 1 over m eventually. So x after a finite stage, all fn of omega will be exceeding x plus 1 over m, and that limit inferior, now you put in the definition, it comes in form of this additional unions and intersections. So put that in, and that turns in terms of the individual descriptions of the fk's. But now these sets that you have at the end, this fk of omega strictly greater than x plus 1 over m, are nothing but pre-images of certain type of intervals, correct? So these sets are already in the sigma field, domain side sigma field, because fk's are given to be Borel measurable. Therefore, as soon as you are allowing these countable unions and intersections in the sigma field script f, you will automatically get these countable unions and intersections to be in the sigma field. So therefore, the set that you have started off with, that was originally for the function g, that was the pointwise limit function, that pre-image must fall inside the domain side sigma field. Okay, and therefore this will imply that all the pre-images for generating sets will be on the domain side sigma field, and hence G must become measurable. So pointwise limit function, if it exists for all omega, all points in the domain, then G must be measurable. So this is an interesting result. So in the above theorem, if fn's are real valued and if this limit exists for real line only, so that means that if the fn's are first of all start off with real valued functions, and if it so happen that the pointwise limits these values for each fixed small omega, if this limit is a real number, so you don't have to consider plus infinity or minus infinity, then the same argument will go through, but then you will have to use this kind of pre-images for open x to open infinity. So these sets are now in the real line. So earlier it was including the infinity, so we had taken open x to closed infinity, but now we are taking open x to open infinity. So these sets are inside the real line, and as long as you go through the exact same structure of the arguments, you will immediately be able to claim that the pre-images are again on the domain side sigma field. So there is not much difference in the arguments. So if you can prove it for the extended real valued functions, and provided the limit function, pointwise limit function is real valued, the exact same argument will go through with minor modifications for the real valued case. Okay, so if you do that, then you can show that G is actually Borel measurable, real valued Borel measurable function. Okay, so the limit function will be, as long as the limit function is real valued, you can show that it is actually real valued Borel measurable function. So with that at hand, you can actually extend these ideas, and I have put it in the format of theorem 3. So in the theorem 3 we had looked at the limit functions, but then there are other such similar functions, and the details are script for brevity. Okay, so what you do, again you take this extended real valued setup, so we'll make a comment about them for the real valued case. So first let's look at the real valued functions setup. So given this sequence of functions, look at the limit superior of the functions, limit inferior of the functions, supremum of the functions, and infimum of the functions. So what are these limit superior? So for each sample point, look at the real valued or extended real valued sequence fn of small omega. So that's the extended real valued sequence, and you can talk about the limit superior of that. Similarly, limit inferior is defined exactly in the same way. You compute the pointwise limits of these functions, and as it happens that this limit superior, limit inferior, supremum and infimum, these functions always exists. So this is slightly different from the case of limit, pointwise limit case. So in the pointwise limit, you have to assume that the sequence converges, and then you are getting the values. Of course, in the convergence sense, you are allowing the infinity or minus infinity as possible values. But here, you don't have to worry about that. So by definition, supremum, infimum, limit inferior and limit superior of functions always exists. But they are now extended real valued. So you can now show using a similar arguments that as long as you take each fn to be Borel measurable, then they also will become Borel measurable functions. So the modification of this as done for the limit functions case will be that as long as you assume that this limit superior, limit inferior, etc., this kind of functions are real valued, then these functions are also real valued Borel measurable functions. So you can just make the modification. But then there was this exercise that we had mentioned in the previous lecture. So this was exercise 5. So there we had talked about a function g. So we had been talking about a function g which we wanted to put in the denominator of a division operation. So there we had taken this g which was not taking the value 0, correct? So this is a similar problem. You go back to exercise 5, you will find the similarity. So what we are saying in exercise 6 here is that you will take g to be Borel measurable in that setup, but afterwards if you are given the information that range of g is actually within R, then can you say that g actually is Borel measurable in the as a real valued Borel measurable function? And the exercise says yes, you can do this. So this was the exactly similar question that was asked in exercise 5. So it was put in the form of a question there. So the answer to that question in exercise 5 is also yes. So the idea is this: as long as you are restricting the domain, so in the domain, if there is this natural choice of Borel sigma fields, you should expect that it will remain measurable, and that's what you are supposed to prove here. So originally it was extended real valued Boolean measurable function, but if you additionally give the information that the range of the function is contained within the real line, then you say that yes, okay, fine, G is actually a real valued Boolean measurable function. Okay, so now this is the comment now we make. So this is a different way of looking at the same thing, that if you assume that the limit functions, this limit superior, limit inferior, or this supremum or infimum functions, if they are actually given to be real valued, then they are also real valued Boolean measurable functions. So there are two ways of looking into it. So one is, if you are given the information before you start working that these functions, limit superior for example, is only taking real values, then you directly work and try to prove that they are real valued Boolean measurable function. But if not, if the information is not given beforehand, what you can try to do is that you first work with extended real value setup, prove that they are extended real valued Boolean measurable function, and afterwards whenever you are given this extra information that the function is actually taking values within the set of real numbers, then you improve upon that. You go from the extended real valued measurability to the real valued measurability question. Okay, so there are two ways of going about it. So only difference is when are you being given the information that the function is taking values within the set of real numbers. Okay, so now we recall another two functions that were discussed in the previous lecture. So we look at this positive part of f and negative part of f. So again you take the maximum between f and 0. So you just look at the values when f of omega is strictly positive. So there you will get the function value. Otherwise, as long as the function f is taking negative values, this maximum becomes 0. So it just looks at the positive part of f, and that's what we call the function f plus. Similarly, function f minus is the negative part of f. So now there are some very interesting properties of these functions f plus and f minus. So some of these were discussed in theorem 1 earlier, that if f is Boolean measurable, then so are f plus and f minus. So this maximum operation preserves measurability, and that's how we got this result that f plus and f minus are also Boolean measurable. Now you can actually show this nice properties, and immediately this will follow. So you just check the definitions, you will immediately get these things. So for example, f plus is a maximum between f and 0, so that maximum is always greater or equals to the 0. Similarly, f minus is the maximum between minus f and 0, and you will immediately get this. Okay, so these are non-negative functions. Statement B says that if it happens that f plus is strictly positive, then what it means is that the actual function is taking positive value. So therefore, in the negative part of the function, you will get 0 as the contribution. Correct? So just check the definitions, you will immediately get this. And exactly the relevant statement, when you exchange the role of f plus and f minus, it's this. So if the function f is taking negative values, so f minus is giving you some positive quantity, then f plus, the positive part of f, will be 0. Again following the same description that we have done in B and C, if you put them together, you can now try to prove this, that if you look at the set of points in the domain where f plus is positive, and if you look at the set of points where f minus is positive, they will not have anything in common. Okay, so the intersection is an empty set. Okay, and then the very important identification that the function f, original function f, can be written as a difference of these two things. So here f plus minus f minus, so original function f is written as f plus minus f minus. Okay, all right. So here it's again important to note that by statement D, you will not have a infinity minus infinity situation. So if f plus becomes infinity, then f plus is positive, then f minus must be 0 there. Similarly, if f minus becomes infinity, then f plus must be 0 at that point, and therefore you will not have infinity minus infinity situation there. Okay, so this is always defined. Okay, and this is an interesting observation that mod of f also can be written in terms of this positive part of f and negative part of f. This is simply the addition of these two functions. Please try to check this. So these are easy verifications that are left as exercise for you, and all of these statements follow immediately as long as you follow the definitions of the positive part of f and negative part of f. So with this at hand, we are now going towards a very important collection of functions. So now, as mentioned earlier, we had looked at three types of examples of measurable functions: constant functions, indicator functions, and in the restrictive fashion, when we were restricting our domain to the real line or some Euclidean space, we had looked at continuous functions. So we have these three types of examples at hand. So now with these putting together, we want to construct more examples, and with the algebraic properties at hand, we can now do the following. We look at something called simple functions. So what are these? So again, we are fixing that measurable space right at the beginning, and look at functions of this type omega to r bar. So either you look at extended real valued functions or the real valued functions. In either case, you say that a function is called a simple function if it can be written as a linear combinations of indicators. Okay. So here you want this finite number of sets a1 to an. They should be pairwise disjoint. They are in the domain and they should be pairwise disjoint. So that's how the indicators come up. And then you want these scalars small x1, small x2, small xn, extended real numbers or real numbers, something. Then you look at this linear combination, finite linear combinations of indicators. You look at such things. So if your function can be represented like this, then you say that it's a simple function. And it's important that these AIs, these sets that you are using, they should be pairwise disjoint. Okay. So now you will immediately look at certain nice properties of these indicators just to understand how these simple functions behave. And we would also like to talk about these measurability questions. So in the definition itself, we have mentioned that these functions are Bodel measurable, but we will explain that in a minute. Okay. So take any two sets such that their intersection is not empty. So in the definition, we wanted these intersections, all these sets to be pairwise disjoint, but if it does not happen, what kind of situations might occur? So look at any two sets A, B on the domain side. Look at indicator of A plus indicator of B. So this is a linear combination. Only difference with the type of things that we have seen in the definition of a simple function is that A and B are not disjoint. Okay, so let's see. But then what you see is that this addition of these two indicator functions, indicator A plus indicator B, can be written as a linear combinations of certain other type of sets with sets being pairwise disjoint. So the sets on the right hand side are A minus B, meaning A intersection B complement, then A intersection B, and B minus A, meaning B intersection A complement. All of these sets are also in the domain side sigma field. Therefore these indicators make sense. And then these indicators, using these indicators, you can write down this combination of functions. You just check that this equality is fine. So put any point in the domain and check that this equality is fine. But what is happening at the end, once you verify this equality, what is happening is that the sets on the right hand side are pairwise disjoint, and therefore the function that appears on the right hand side, that is a simple function. But then originally I did not start with sets which were pairwise disjoint. So what does it tell you? It says that given finite linear combinations of indicator functions where the sets need not be pairwise disjoint, you can rewrite this same function as a linear combinations of the indicators such that the sets are pairwise disjoint. Okay, so start with some linear combinations where the sets are not pairwise disjoint, but split them up into the appropriate intersections. So intersections of A and A complement, B and B complement, and so on. If you split them up, if you start with such finitely many sets, you can go to these intersections of all these many sets and including their complements. You can write down this equality of this addition, that linear combination, in terms of another linear combination where the sets appear with these intersections, indicators of intersections, and they turn out to be pairwise disjoint. Okay, so even if you start off with some linear combinations of indicators where the sets are not necessarily pairwise disjoint, you can rewrite it and in terms of certain other sets where they also appear as a linear combination of indicators where the sets are pairwise disjoint. So therefore the restriction of pairwise disjointness is not that severe. You can simply add up indicators, and as long as the summation makes sense, you can get a nice function. Okay, so as long as this addition of two simple functions is defined, you can rewrite things in this form. Okay, so what do I mean by this addition making sense? Infinity minus infinity situation should not appear. Okay, so we want, as long as the infinity minus infinity situation does not appear, you can talk about addition of functions. This is anyway pointwise addition. So pointwise addition will make sense as long as infinity minus infinity situation does not appear. Okay, so as long as that happens, you can obtain the simple functions. Okay, now another important observation now about the comment about measurability of such functions is that this indicator of A will be Borel measurable if and only if the set is in the domain side sigma field. But then you recall that constant functions are also Borel measurable, and therefore if you look at the multiplication of measurable functions, it's also measurable. So here we are multiplying the constant function C with the indicator. So therefore again by theorem 1, linear combinations of those also will be Borel measurable. Okay, addition of measurable functions will be Borel measurable. So that's the idea that is being used here. Okay, and another interesting comment is that whenever you are looking at these simple functions, you can, without loss of generality, assume this additional condition that the finite union of these sets that you are using in your definition of simple functions, that it covers the whole set. So why? Because if you are looking at this finite union, and if it is a proper subset of omega, then you can look at the complementary part of that and think of it as the n plus 1th set. Okay, so originally you are given n many sets, and I am saying just add one more set to your collection, which is the complement of whatever the sets before was. Ignore all those things, look at the complement. So that will give you the n plus 1th set. So the complement of the first n sets unions complement. Okay, great. So now rewrite the linear combination by adding this extra set, adding this extra term in your collection. So what is this? Originally the terms were n many, so you had n many terms, n many functions you were adding up, but then you can simply think of the term coming from the n plus 1th set with the scalar 0. Okay, so this will summation again will make sense because you are just adding 0 everywhere. Okay, so this will be the exactly the same function, but here the union of the sets will be the whole set omega. So again, without loss of generality, in a simple function description, you can always assume that the sets you have, they are pairwise disjoint and they are covering the whole domain. Okay, alright. So again, this is an important clarification once more. So again, simple functions as defined, if you are talking about extended real valued simple functions, then they are allowed to take the values plus or minus infinity. As long as that summation makes sense, as long as infinity minus infinity situation does not appear, you can define simple functions. Okay, but in practice we are going to work with simple functions which actually take values in the real line. So you will see the reason why. Okay, so we are going to look at finite linear combinations of indicator functions, which are these simple functions. Those scalars that appear in the as the coefficients of the linear combination, they will be taken to be real numbers. You will see the reason why in the theorem 4. So what is this? So this is approximation by simple functions. What it says is that general functions by some appropriate mechanism can be approximated by simple functions. You start with extended real valued functions, but then as stated earlier, you can also restate these results in terms of real valued functions. So again, if your original function is real valued, you will get the exact same result. Okay, so real valued Borel measurable functions anyway are extended real valued Borel measurable functions that we have left as an exercise earlier. Okay, so you could always apply this result for real valued Borel measurable functions. Okay, so there are two parts to this theorem. So what do you do first? So suppose your f takes only non-negative values. So your f is a non-negative Borel measurable function. Then you can find a sequence fn of real valued non-negative simple functions such that the simple functions increase pointwise and their limit is f of omega. Okay, so there are a lot of things to digest here. So first of all, you are starting off with a non-negative measurable function f. I am saying you are getting a sequence of simple functions. These simple functions first of all are real valued. You don't have to look at extended real valued functions, and they take only non-negative values. That's also an important information about this sequence of functions. If you look at the graph of the function f, so that is a non-negative function, it's above the value 0, and what the simple functions are doing are it's approximating it from below. So fn is increasing, fn of omega is increasing for each n. As long as you increase the n, it will give you slightly bigger value. So and then at the end it will try to approximate the actual value of the function f omega. Okay, so these functions are increasing in n. Pointwise limit being the given function that you have started off with. Okay, so you have this sequence of non-decreasing functions, simple functions, real valued and non-negative. Okay, so this situation we usually write it as fn increasing to f. So as long as you have a sequence of increasing functions, you can write it in this way. Okay, all right. And the second half of this is for general measurable functions which could take positive and negative values. Okay, so here we are saying that if you are having this function, then again you will get a sequence of simple functions. These simple functions will no more be non-negative, they will be now real valued. So again you are restricting your attention to only real valued simple functions, such that you have a different condition on the sequence now. So this fn of omega will be in modulus, will be dominated by modulus of f. Okay, so for each n and omega, these functions are bounded above by mod f. Okay, so that's basically the idea. So for the non-negative measurable functions f, you can get an approximating sequence that approximates the function from below. In the general functions case, you get a sequence. Again, it will turn out to be a pointwise limit, but then you get a different bound for the approximating sequence. Okay, so how do you prove this? So consider the case of the function, the given function small f, when it is non-negative and measurable. So here we are supposed to figure out a sequence of functions fn which are simple functions. So therefore they are defined on the given domain omega, taking non-negative values. So for the moment let's just write them as real value, but you would like to specify non-negative values for these functions. And we also want to show that pointwise for every fixed sample point, the function values fn converges to the given function value f of omega. Okay, so that's what we are going to do. So this is what we are going to construct explicitly. So how do you do? So you first fix a integer n and look at a sample point small omega. So now if the actual function value f of omega is exceeding that integer small n, if it is greater or equals to small n, then you specify the function value for the approximating sequence as n. What remains? So in that case, f of omega takes values between 0 to n. So closed 0 to open n. What do? You split this interval closed 0 to open n into 1 by 2 power n length subintervals. So how many such intervals you are going to get? You are going to get n times 2 power n many such subintervals. These subintervals will be from k minus 1 by 2 power n to k by 2 power n. So k minus 1 included, k by 2 power n excluded. So these are left closed, right open intervals. And if you look at for all possible k like this, so 1, 2, 3 up to n times 2 power n, then you are going to cover that interval closed 0 to open n, right? So now what do you do? So you look at the actual function value f of omega. It is now in closed 0 to open n. So then in particular it will be in one of these subintervals for some fixed k. What do? You specify the function value for the approximating sequence for that sample point as the left endpoint value. So we will see why we need this, but we specify this as the left endpoint value k minus 1 by 2 power n. So that's your function fn. For each function value, each sample point, you have defined the function value fn omega. Okay. So now you are going to check whether you have defined it for all possible small omega. Observe that the original function small f is non-negative valued. So you have the function values taking between 0 to infinity, infinity included. Okay. So therefore what will happen is that you are basically going to split the interval 0 to infinity included, that range of function values for the original function small f, into these intervals. So one of the intervals is n to infinity, so closed n to closed infinity, so that's one interval, and the interval closed 0 to open n, you have split it into these parts. Okay, so that therefore you have considered all possible values of the function f, and therefore you have considered all possible sample points on the domain side small omega, right? So therefore you have defined it for all possible sample points small omega in your domain. So fn is well defined now. Okay, but I am going to claim that this is a simple function. What is the reason for this? So the reason for this is very simple. So when you are looking at the original function value from this left closed right open intervals, you are just rewriting this condition in another format. So you are simply saying that the function value f of omega lies in this interval closed k minus 1 by 2 power n to k by 2 power n open. But you can write it in this different format, that omega belongs to the pre-image of this left closed right open interval, correct? So on this you have specified the approximating sequence fn value as k minus 1 by 2 power n. On the rest of the portion, when your function value is from n to infinity, so you are looking at omega as it belongs to f inverse, the pre-image of this thing, right? Pre-image of this interval. So therefore on that interval, on that pre-image, you are specifying the value n. So therefore you are now going to rewrite that conditions in terms of indicators. So that's as simple as that. So as long as omega belongs here, this indicator will supply you the value 1, otherwise it will supply you the value 0. So all these intervals k minus 1 by 2 power n to k by 2 power n, so for different values of k and n to infinity, that interval, these are all pairwise disjoint intervals. So their pre-images are also pairwise disjoint, and therefore this collection that you see here, it's basically splitting up the domain omega into all these pre-images of the original function small f, right? So that's what we are doing, and all these individual pre-images we are specifying the function values of fn. So now we have written it in terms of indicators which are all involving pairwise disjoint sets, and it basically covers the whole domain. So therefore you have written the original function fn of omega in terms of these combinations of indicators, and therefore this is a simple function. Now it's a easy fact to check that for n and n plus 1, the simple functions that you are going to get, fn and fn plus 1, these values can be compared. So how do you do this? So to do this, what you need to do is to look at the function values for n and n plus 1, look at the corresponding function value f of omega, and just compare the corresponding prescribed value. And in the corresponding prescribed value, the nice thing is that you are approximating the actual function value f of omega by this left end point, right, of the interval. So therefore you are making an error of at most 1 by 2 power n. So that's why it's also the approximating sequence. As n increases, your error decreases. So that's the error that you are looking at here, the difference between these two values. Okay, so you can check this increasing properties. And by definition, of course, this fn, the functions, simple functions, are taking non-negative values. So that's by definition. So but it's important that these functions fn are not taking values in the extended real numbers. These are not taking the value plus infinity, right? So even if the original function small f is taking the value plus infinity, you can approximate it by real valued non-negative simple functions here. Okay, so that's the proof of the first part. Great. So now what was the second part? Second part was for general measurable functions which could be taking values plus or minus infinity. Okay, and they could be taking positive or negative values also. Okay, so here what we have observed earlier is that we could write the function as f plus minus f minus. So this we have discussed a few minutes back before discussing this theorem. So now these two functions f plus and f minus are non-negative measurable functions. So for these two individual functions f plus and f minus, by the first part you can now construct this sequence of functions gn and hn, each of which will approximate it from below, and these gn's and hns should be simple functions, right? So this is by the first part. So f plus and f minus are non-negative measurable functions, and therefore you can do this. But then you observe that gn's fall between 0 and f plus, and hns fall between 0 and f minus. That's simply by the conditions. And then you can talk about this difference now. So gn minus hn. So if you look at gn minus hn, gn approximates f plus, hn approximates f minus. So therefore their limit value will be actually f plus minus f minus, that will be f of omega. You can try to check the details. So the idea here is this: for each fixed n, when you are looking at gn minus hn, it will not happen that both of the functions gn and hn are positive. So for each fixed n, if you look at the point small omega such that gn omega is strictly positive, hn omega is strictly positive, that will be an empty set. Okay, so here you will not have an infinity minus infinity situation. So therefore this difference is making sense. So the limit will make sense because pointwise limits for gn and hn make sense. So you will get the function f of omega because gn approximates f plus, hn approximates f minus. Okay, so therefore you get this difference gn minus hn. But then this gn minus hn, let's call it fn. But then as we have mentioned that this is now nothing but a linear combinations of indicators. Gn was a simple function, Hn was a simple function, so each of which are linear combinations of indicators. So if you are looking at Gn minus Hn, it's also a linear combinations of indicators. So therefore Fn will turn out to be simple by appropriate adjustment that we have mentioned earlier. Okay, and then finally you can check this condition that mod of Fn, which is Gn plus Hn. Okay, so you can check this, why this is happening. But then Gn will be dominated from above by F plus, Hn is dominated from above by F minus. Add them up, you get mod F. So this was also mentioned earlier in a note 17. So please check this, why this is true. Okay, why this equality holds. Okay, so with that we have completed the identification that given a non-negative measurable function, you can get this approximating sequence of simple functions non-negative which approximates the function from below. If you are having a real valued or extended real valued function taking positive or negative values, in which case you will get a approximating sequence, again real valued, but it will no more be non-negative. Alright, so another important observation is that if you go through the proof, you can actually try to show that if a original function is given to be bounded, so if it is real valued and it's bounded, then you can actually show that this pointwise convergence of these simple functions is actually infirm. Okay, so these fn's that you have constructed, they will actually give you a uniform approximation to the function. We now discuss certain exercises. So if an is an increasing sequence of sets, look at the union A. Now you can ask whether indicators of an increase to indicator of A. Okay, so these are all non-negative functions. You are asking whether indicators of an increase to indicator of A. Okay, so please check this. So now one final comment as we stop. So while proving this general properties of measurable functions, you have this general principle of working with such functions. So in case you are unable to verify the required property directly for all measurable functions, what you should do is to following approach. First you prove it for indicators or simple functions. Then you go by approximations and prove it for non-negative measurable functions, because non-negative measurable functions are now pointwise limits of simple functions. So you hope that your property will be carried over by this pointwise limits. And finally you approximate it for measurable functions, because measurable functions are now difference between two non-negative measurable functions. So as we have observed, if f is a real valued or extended real valued measurable function, f you can write it as f plus minus f minus. So if you prove it for f plus and f minus, you hope that whatever property you want also holds as you take the subtraction between these two. Okay, so this is a general principle that will be used in discussions later on in this course. Okay, so this is a general property that is also helpful in proving other properties. Okay, all right, so we stop here and we will continue this discussion in the next lecture.